Hi there. We're going to go over our pharmacodynamics quiz so that you're all prepared for the exam coming up on Tuesday. So, rapid development of tolerance to a drug would cause what? Well, usually, right, as we consider our concentration effect relationship, as the concentration goes up, the effect will go up, yes? And as the concentration falls down, the effect would fall down. But in this case, as our concentration is going, I'm going to erase that. Whoops, that's not what I want to do. I'm going to try to erase that if I know how to erase. I don't see the eraser on here. Anyway, as our concentration goes up, our effect goes up, but and then as our concentration still goes up, our effect starts to go down, doesn't it? Even though our concentration is going up, our effect is going down. So as time goes on, the concentration goes up with the effect as we would expect, but it continues to go up and the effect starts to go down. That's what we would see with a development of tolerance, isn't it? Our effect would start to wane or decrease. So this is called a hysteresis. And since it's traveling in a clockwise direction, our answer would be a clockwise hysteresis. And really, rapid development of tolerance or some sort of waning of receptors is how we would see a clockwise hysteresis. How do we see a counterclockwise hysteresis? As the concentration goes up, maybe I'll switch colors. Can I switch colors? Oh, there's the eraser. I'll switch colors. As the concentration goes up, the effect goes up, but the concentration starts going down and the effect still goes up. This is a counterclockwise hysteresis. What causes a counterclockwise hysteresis? Well, some sort of a time lag, which is often due to an active metabolite or a effect compartment. So the drug has to travel to a certain point, like to the heart muscle or to the CNS or something, to have its effect. And then the other is a turnover model. So that's like where you have to get rid of something that's already in the body. So there's a lag in time. So, and a good example of this that we talked about was warfarin, right? Where you have to, the way it works is by inhibiting the formation of the vitamin K dependent clotting factors. Okay, good. Slow distribution, whoopsie. Slow distribution of a drug to the site of action. So this is slowly distributing the drug to the site of action, not slowly distributing the drug to the blood, which is what would happen with an extended release or a slow release medication form. But this is slow distribution of a drug to the site of action. So we just talked about that. That would be a lag, which would give us a counterclockwise hysteresis, right? Change it to red. All right. A drug following a linear pharmacodynamic model. Okay, so a linear pharmacodynamic model is where we have an Emax model, which is E is equal to Emax times concentration all over C50 plus concentration. And remember, this C50 and the concentrations would have a gamma here that is the slope effect, or some people call it the Hill constant, that is going to be in a sigmoid Emax model. But our simple Emax model, gamma is equal to 1. And to make it linear, this is not linear. To make it in the form of a line, we would have to see concentrations that are much less than C50. So this concentration term falls out of the equation, and we have E equals Emax times C over C50. So the linear model is Emax, and it's approximately equal because this is only approximate, times C. So this isn't a linear form, right? Y equals, and this is M, and the C is X, right? Because we're looking at a graph that's concentration versus effect. I better change my color there, right? Maybe I'll try blue. Concentration versus effect. So the Y value and C is the X value. And the slope of this line is Emax over C50. So what's our question here? The drug following a linear pharmacodynamic model will have a gamma of 1. Yes, we know we have to have a gamma of 1 to make sure that we don't have a sigmoid Emax model. And concentrations that are much less than C50, that's true. Concentrations have to be much less than C50. That's our second thing. So true, true. The slope of the line describing E versus C will be Emax over C50. Absolutely true. Awesome. All three things are true. Okay. Drug whoosh follows the attached pharmacodynamic model. The therapeutic range is between C20 and C80 for this drug, and the T1/2 is 3 hours. What's the longest dosing interval possible? Okay, let's see. So here's our attached model. Okay, so the therapeutic range is between C20 and C80, and the half-life is 3 hours. Okay, so what's our C20? I'm going to change from blue because that's blue on our C20. So we go to our 20% effect, and we see where our concentration is. So our minimum of our therapeutic range is 10. If we go to C80, our maximum is 40, isn't it? So our therapeutic range is 10 to 40 milligrams per liter. All right. And the half-life is 3 hours. Oops. The half-life is 3 hours. What's the longest dosing interval possible? Okay, so we're going to go from 40 to 10. So how long can we stay within 40 to 10? All right, well, there's a couple ways of figuring this out. We want to get a guesstimate. So the half-life is 3 hours, right? So we know if we go from 40 to 20, that's one half-life, and another half-life will be 20 to 10. So it's actually, we know it's 2 half-lives. So if the half-life is 3 hours, it's a 6 hours is the longest it can possibly be, right? So, yep, it's going to be 6. The answer here is 6 hours. Oh, I can't write it, but you guys know. Okay, so the longest possible is 6 hours. Now, we could do it another way. We could use our equation, concentration, oopsie. Concentration at time t is equal to concentration at time 0. These are just relative things, times e to the negative kt. All right, so we know that our C0 in this case, we want to know how long it's going to take to go from, so I'm going to write a little graph here, from 40 to 10. So we know here's our initial concentration, here's our final concentration. We want to know what this time difference is here, right? So our CT in this case is going to be what? Our CT, our concentration at time t relatively here is going to be 10, isn't it? And our initial concentration relative to that is going to be 40, isn't it? And then E is E. What's our K going to be? Well, if we know our half-life is 3 hours, don't we know that K is equal to 0.693 divided by 3 hours divided by our half-life? So that's what I'm going to put in here. K is negative 0.693 over 3. So let's do our math. I'm going to erase this here. So first thing I'm going to do is divide 10 by 40, which is 1/4, which I don't need my calculator for, 0.25, sorry, is equal to E to the negative 0.693 over 3 times T. And we're solving for T, aren't we? So what do we have to do? We have to take the natural log of both sides. So the natural log of 0.25 is negative 1.386. And the natural log of this side is going to be E, or I'm sorry, brother, that's the whole reason we got rid of this, is negative 0.693 divided by 3 times T. We're solving for T, right? So those negatives become positives. So we multiply 1.386 times 3, and then divide that by 0.693, and we have a T of 6 hours, which we knew already, but either way, you can do it either way. You should be able to do it either way. Now, it's not very common that it comes out so even like that, but I was being nice, wasn't I? Okay. If new drug Shazam, see the attached graph, has a therapeutic range again between C20 and C80 and a half-life of 8 hours, if the patient takes more than usual and has a resulting Cmax concentration of 100, how many hours will it take until the drug reaches the high end of the therapeutic range? Okay, so the first thing we need to know is what is the therapeutic range? So C20 again to C80. Okay, so C20, again, it's 10 to C80, which looks like it's like, we're going to say 25. Could be 24. I don't know. If we knew the equation, we could figure it out, but I guess we could guess the equation or whatever here too. So anyway, so we're going from, we want to get to 25. So how long until we get to 25 milligrams per liter? We need to go till we get to the high end of the therapeutic range, which is here, right? So if we're at 100, we're starting at 100 milligrams per liter. Again, it was easy on you, wasn't it? 100 to 50 for one half-life, 50 to 25 for two half-lives. Two half-lives. And what's the half-life is 8 hours. So the answer here is 16, isn't it? Yep, it's 16. Now, what if you were using your equation? Again, let's draw a graph. Our concentration time curve in this case is going from 100 to 25. And so we want to know this time difference, don't we? From time 0 to time t. So our CT equals C0e to the negative KT. CT in this case is 25 milligrams per liter. C0 is 100 milligrams per liter times e to the negative k, which in this case, again, our half-life is 8 hours. So our k is going to be 0.693 divided by 8, isn't it? So our k is, I'm going to erase this here. Oopsie. 0.693 divided by 8 times t. And again, 25 divided by 100 is 1/4, which is 0.25. This equals e to the negative 0.693 over 8 times t. Take the natural log of both sides. And I forgot what it was already here. 0.25 natural log is negative 1.386. And the natural log of this side is negative 0.693 divided by 8 times t. Again, those negatives become positives. We multiply 1.386 times 8 divided by 0.693. And we get 16, just as we thought we would. Okay. Please list circumstances that might cause a drug to exhibit a counterclotted hysteresis. I guess we already talked about this one. So it's going to be a lag in time between the concentration and the effect. So it could be an effect compartment that the drug needs to move to, or an effect tissue that the drug needs to move to. It could be that it's a prodrug, or that there's an active metabolite, or it could be that we have a turnover situation where, like warfarin, where the way it works is by inhibiting vitamin K dependent clotting factors. So you have to wait until those the current vitamin K clotting factors are no longer there. Okay. Pharmacodynamics is the study of the relationship between the concentration and the effect of the drug. Well, whoopsie. I don't know how I did that, but can I go back? Okay, I don't know what I did there, but I hope this will work then. Pharmacodynamics is the study. Can I get rid of those? And make that bigger. Yes, okay. Pharmacodynamics is a study of the relationship between the concentration and the effect. Well, it is between the concentration and effect. What we really want to know is what dose rate do we have to give to get an effect, right? And what we've been studying up for most of the time is what dose rate do we have to get a certain concentration. And then making sure that that relates to the effect, right? This is what we really want to get to, but we have to do this by combining kinetics and dynamics. And yes, dynamics is the relationship between the concentration and the effect. We've constantly been looking at this graph, right? So it's about the relationship between the concentration and the effect of a drug. So yes, this is true. In the sigmoid Emax model, the larger the gamma, the steeper the slope of the sigmoid concentration effect curve. Yes, right? The larger the gamma, the steeper that, let's see if I can make a little graph again. This is where the sigmoid part really comes in. It's sometimes called the Hill constant, or the slope factor. So we could have drugs that all have the same C50. C50. So if this is our C50, but have very different, I'm terrible at this. And they all go through the same point, but have different slopes. So they all have the same 50, they all have the same Emax, but the slope factor is different. And the larger the gamma, the more steep this is. Okay. So yes, this is true. The steeper the slope of the sigmoid concentration curve. And if you so the therapeutic range is going to get smaller and smaller, right? Because there's going to be very little difference in effect when you go from this concentration to this concentration, or there's going to be a large amount of effect between this concentration and this concentration, and you'll get to the top really quickly. So yes, you're going to have a smaller therapeutic range when you have that steep curve. So this is true. I didn't do a very good job of picturing that. Hopefully you understand that by having it steeper, that the concentration range is going to get smaller. The new drug Springy, see attached graph, has a therapeutic range from C20 to C80 with current dosing. Your patient has a measured CSS average of 40 milligrams per liter and of max of 40 and a min of 10. So they're at steady state and their Cmax at steady state is 40 and their Cmin is 10. Is this patient appropriately dosed? So basically we're trying to find out what the therapeutic range is and making sure that 10 and 40 makes sense, right? So C20, in this case, C20 is, I don't know, 4 or something like that. So 4 milligrams per liter. And C80 is 50. I'm going to go with 50. Is 50. So the therapeutic range, maybe we'll say 5 and 50 just for, to make it a little easier to deal with. So the patient is between 10 and 40. So yeah, they're in the therapeutic range, aren't they? So the answer to that one is yes, true, yes. All right. Drug A and B act on the same drug receptor. Drug A has an Emax of 100, a C50 of 20, and a gamma of 3. Drug B has an Emax of 100, a C50 of 5, and a gamma of 1. So before we even go on here, what can we tell about these two drugs? Well, drug A has a steeper slope, doesn't it? And it has a C50 of 20. And drug B they both have an Emax of 100%. And here the C50 is 5 for drug B. Drug B has a smaller C50, which means it has a higher affinity for the receptor, which means it's more potent, right? But has a more gradual slope. Which drug is more potent? Okay, B. All you have to do is compare the two C50s. That's an easy one. All right, that's it. I hope if you didn't understand it when you took the quiz, you do now so that you can be rewarded on the midterm. All right, thanks.